So today I'm very excited to announce our first keynote speaker. Niko Matsakis has been a senior researcher at Mozilla and a core member of the Rust team, where he worked on the initial, a lot of the initial work on the type system and other important features. He's been working on Rust for about 6 years. Previously, he did his undergrad at MIT and completed a PhD at ETH Zurich in 2011. And he also spent some years at Data Power Technology, since acquired by IBM, where he worked on a JIT compiler and networking runtime. So everyone, please help me welcome Niko.
Thank you very much. So yeah, I'm here to talk today about Rust. As Jackie just said, I've been working on Rust for about 6 years, but what she didn't mention, because I didn't tell her, is that before that I have been a pretty big fan of C++ for a long time. I distinctly remember asking my parents for this book. Must have been middle school for a Christmas present, and I poured through the whole thing. I couldn't find a picture of me reading it though, but I did find this, of reading the Zen of graphics programming with my dad at some point or another. Which I thought was pretty cool. But I'm here today to talk about Rust. And so I know not everybody here is familiar with Rust or even heard of Rust, at least based on some of the conversations I had so far. So I thought I'd give a kind of really quick intro to what Rust is at a very high level. All right, so the basic idea is we want to take all these nice safety guarantees that you can get if you write a program in Java or C# or some other language like that you're not going to have double freeze and segmentation faults. In fact, we want to go further and say you also won't have data races, so your parallel programs will be more predictable, and have a type system that's more expressive that can help you get correctness guarantees, or not guarantees, but get correctness beyond these basic guarantees. Well, we want to do all of that without having to have a runtime or a garbage collector, or really any undue performance overhead. So I've heard Bjarne Stroustrup say that C++ tries to leave no room for a language between it and assembly. Rust kind of has a similar ambition, right? There are people writing kernels in Rust and so forth. So I think overall, basically, our big goal is that we want to have productive systems programming, and I mean productive in a kind of global sense. So how fast can you get your program up and running? How fast can you meet your performance requirements? But also, how well can you maintain it over time, right? Because that can be a big productivity drag. And today is kind of a good day to do a talk on Rust because it's almost our 2-year birthday, so to speak. We had our 1.0 release, 2 years ago, on May 15th, so yesterday. And in that time, Rust has been growing. We've got a lot of people using it in production now. I have a partial list here of the most kind of biggest names, but you can see a more complete list on our webpage. So, of course, Firefox has started to integrate it. And I say of course because Mozilla sponsored Rust, but actually it wasn't a given that it would A, succeed, or B, make it into Firefox. We had to kind of prove our way there as well. And Dropbox has been using it on their servers and recently also on client side. NPM has integrated it. And GNOME hasn't actually put anything into production, but we've been working a lot with the GNOME team, and we're kind of excited to see where that might go. And there are some GNOME libraries starting to experiment with Rust. So, in honor of Rust being 2 years old, though, I thought I would start with something 2-year-olds love, which is I would tell you a story. And this is a true story, although not exactly as I present it here. And it's a story about using Rust. Right, so it starts at a working place, at this office center where Lady Ada comes every day for her job as a programmer, except something seems dated. Okay, this is better. So it starts at this cafe, right, where every day Lady Ada comes, and she works on her program. And what her program is a compiler. So I told you it was a true story from my life. And she's trying to make it go faster. And she notices that, hey, there's this one main thread that's doing most of the work. And every once in a while, an event occurs. And when this event occurs, we have to update this data structure. And sometimes it takes more time, and sometimes it takes less time. But the key thing is we don't need the result until the very end from this data structure. So this is what gives her an idea. She says, I could probably make this go faster if I introduced another thread, right? I could have, now when the event occurs, I'll just do some lightweight processing to send it off, let the other thread update the data structure, which I don't need to use, and that will take some time. And at the very end, I'll get the result back, right? And if all goes to plan, everything should be faster, right? Because the two threads each have less work and we have more than one core. So she puts this plan in place, builds the system, and it works. And, she feels pretty good. And the thing is, 6 months pass. This has been working in production. The compiler is somewhat faster than it used to be. And then she's doing something else entirely. And to be honest, she's completely forgotten that there were threads in the first place, right? So she's just working on some part of the compiler that happens to be modifying that same struct. This, by the way, is Rust syntax, but I figure you can probably figure it out. So this defines a struct. And this event that happened to be the thing that was getting processed, previously it just had a few integers in it. But now she has to add something new, which is a name, which is an intern string. And this is where the story gets a little bit scary. So if you've done kind of multi-core programming or parallel programming, at least if you're like me, your heart starts to race when you think about all the things that could be happening now. Because what Ada doesn't know about that intern string, she's never actually had to look at that part of the compiler in detail, is that this is how it's implemented. And this RC of string, that's kind of rough speak for a reference counted string, kind of like a shared pointer, except RC is not atomically reference counted. So that means that if two threads come along and try to modify the ref count in parallel, it could be wrong, right? And in particular, like I said, we did just introduce this thread that was going to send these events and hence send intern strings across threads. So there's a pretty good chance that we're going to be modifying this ref count in parallel. One of them will probably get slightly off. This probably won't cause a problem right away, especially because these are intern strings. So there's always kind of one big dictionary holding it, at least one ref. But sooner or later, it's going to cause a crash, or maybe just gibberish output or something, right? And it's going to be a big pain and waste a lot of time to debug. But actually, none of that happened, right? Because she was using Rust. So what actually happened was that she got a compilation error. And she said, what? So the type intern string does not implement send. That's kind of Rust speak. We'll get to it in more detail later for saying this is not a thread safe type. And she said, why would it have to be thread safe? Oh, right, I have a thread. I forgot about that. And then she went in and changed it, and everything was fine. And this is kind of the experience that Rust is aiming for, that you can do things very easily to start, right? So you notice it took her only one day to put those threads in. That's also really the story is about me, so I'll switch to the first person now. It took me about one day to put those threads in the first place, but that's only part of the cost, right? The rest of the cost comes later in the maintenance period. And where Rust type system is really great is when it can kind of deflect these things that would have been very painful, and it will only take 5 minutes of your day now to fix it and get the rest of the system back going, right? So there's kind of these two parts. The productivity in the beginning and the productivity in the end are the things I want to kind of drill into more. I mean, I think the productivity in the beginning comes from in large part from the zero-cost abstraction idea that Rust has kind of learned from C++, right? So we've got a lot of libraries that let you write code that's very high level and that compiles down to something very efficient. So this first example is a function that tests if a slice, or a string slice we call it, is all white space, right? And we can do that by calling text.cars, which will give us an iterator over characters, which is kind of like a C++ range. We can call .all, which invokes a closure on every character. And this is the closure syntax in Rust. So we're saying for each character C is C white space. And that compiles down, of course, to just a little loop with a pointer kind of bumping along this UTF-8 string, right? And this actually was a real-life example from some people who were porting Ruby code, and they had replaced like pages of C code that was doing the same thing with this two-line loop, and it performed the same, and they were very excited. So the load images, this is another example doing parallel processing using, in this case, using a third-party library called Rayon that I'll come back to a few times. It's something I wrote, but it's for doing fork join parallelism. And you see that it uses also iterators, similar idea, except you just write par iter, and now you get a parallel iterator that's executing in parallel, but it's also guaranteeing data race freedom at the same time, as we'll see later. And all of these libraries, basically Rust is a language geared around writing cool libraries that let you write high-level things that perform well, but the best libraries in the world aren't that much use if you can't easily use them. So we also have a nice package manager which lets you find the libraries and add a few lines of code and then the compiler will download them and build them for you and so forth. So that's all part of the productivity story. Right? But that's the first part. That's just the writing code to begin with. Then comes the safety and the freedom that lets you maintain it over time. And that's more what I'm going to focus on in this talk, because that's kind of the thing that comes on top of C++. And I think if you put these two together, that's when you really get to this goal of productive systems programming. Right? So the structure of this talk, I'm going to start with a fairly technical part. I'm going to go through some parts of the language, how they work, and so forth. And I'll focus on kind of the safety, the generic programming aspects, a little bit about parallelism. Don't worry about that unsafe thing. We'll talk about that. And then I'll get to some about what it feels like to use Rust kind of outside of the technical parts. Like, what was it like to get Rust into Firefox? And what are some of the community processes that Rust uses to grow and develop? So let's start with the memory safety. So this was our goal. And the interesting thing about these top two bullet points, the zero-cost abstractions and the memory safety and data race freedom, is that they're actually kind of in tension. There's a reason that a lot of languages that have safety don't also have zero-cost abstraction. And I'm going to start by looking at some C++ code to kind of show you what I mean. So here, this is a few lines, right? Already in these few lines, we see some of the features that let you build zero-cost abstractions effectively. Like we can make full use of the stack in C++. We can put the vector of strings has the fields of the vector are inlined onto the stack, and similarly the fields of the string are inlined into the vector. So all in all, when I want to get to my character data, it only costs me 2 pointer dereferences. Right? And that matters a lot if I'm going to put this vector inside of a hash map and put an iterator on top of the hash map and put something else on top of that. All of those layers start to add up if you have to add a pointer at each point. But once you have the idea of a string being embedded in a vector or what have you, you also need the ability to have a reference right into the middle of other data structures. Right? To have a reference that takes a pointer of a field or of a particular array element. So this is something, of course, C++ has. And once you have that, if you then layer on top of it deterministic destruction, meaning we're going to free the memory of this vector as soon as we exit this function, right? This is where things start to get a little bit complicated. And so if I extend the example now, well, I will just say, however, this makes things complicated, but it is crucial to kind of maintaining your memory use over time and keeping things from ballooning out of control. So if I extend the example just a little bit, we can start to see some of the safety problems, right? This is the same code. I have my element, or not the same, extended version of the same code. I have my element pointer reference pointing into my vector, but now I'm going to call vector.pushback, right? And at this point, if the vector is at capacity, we could have a problem because we'll copy over the old memory, we'll put the new value, and then we're going to free the old memory and adjust our data pointer. And from the point of view of the vector, everything's fine, right? All the references are up to date, everything is consistent. But there's this dangling pointer out here, this dangling reference of element that's pointing now into freed memory. And if I go on and use it, I can get into trouble, right? And even in this simple example, we see kind of the outline of what all memory safety issues boil down to. And there's really two key ingredients that come together. The first is you have to have some sort of aliasing. So you have to have more than one path to reach the same memory. In this case, we have the elem reference and we have the vector's data pointer. Right? And then you have to have some mutation because that's what makes things get freed. That's what changes types, like in a union or something. This is what kind of invalidates references. And the reason these two things combine is if you only have one path to a given piece of memory, it's pretty easy to keep it up to date when you make a change. Right? So if you, for example, update the vector kept its data reference up to date, but it can't keep track of all the elements, all the references that are out there in the world. So what Rust tries to do is to layer on something we call the ownership and borrowing system. And basically, the key idea here is if aliasing and mutation together are the problem, then let's just not have them happen at the same time. And we do this by having kind of three main ways to access data, which I'm going to go through let's call it one by one. Right? So the first one is ownership. This is the most common thing, where you just own some data. And in that case, we're going to see that you don't have any aliasing because you own it. You're the only one who has access to it, but you are allowed to mutate it. Right? Ownership, we chose this word, well, partly because it's in use, but also I think well, you have a pretty common sense feeling for what it means, right? So in life, if I'm owning and I have a book, it's my book, it's on my bookshelf, and I can do a lot of things to it, right? I can write in the margins, I can read it. But one of the things I can do with it also, when I'm done with it, I can give it to somebody else. And now it's their book, and it's not mine anymore, and I have nothing more to do with it, right? And that's kind of how data structures work in Rust. So here's some Rust code. And it starts out by creating a vector. Now, this is our first glance at Rust syntax, so I'm going to just point out a few things. The functions begin with fn. We're from a company that's very familiar with JavaScript, where the function keyword is function, and it's very long. So we tried to make this one very short, since you type it a lot. And then inside of a function, you can declare local variables with let. And this vec : new, that's invoking basically a static method, essentially. New is not a keyword. It's just a method that, by convention, creates an instance of the type it's attached to and returns it to you. So the representation at runtime will be exactly the same as C++. We have our fields on the stack. And I want to highlight this mute keyword. In Rust, you'll see most things tend to not be mutable unless you say so. In this case, we're declaring that we are allowed to write to this book and the data that it owns. And that's kind of a helpful thing when you're reading code. You can see pretty quickly what's changing, what's not, and so forth. I'm going to indicate that with the little pencil there. So when I call book.push, I get data living in the heap, some strings or what have you. So far, it's pretty much the same as what we saw before, but where things start to be interesting is here. When I call publish, you see that it has an argument, which is vec of string. So if you have a function that takes a vec of string in Rust, it's saying, I need ownership of this argument. Give me a vector all for my very own. And on the other side, the default then is to say, well, I have a vector, you want a vector, I will give it to you, right? It's not mine anymore. So at runtime, what that means is we copy over the fields that are on the stack, and the data sort of transfers with that, ownership transfers along. And then we kind of forget about these fields, as if we didn't have them, right? So now publish can execute. It owns the book. It has the only access to this book. It can read it, and when it's done, everything that it owns, it can free, right? It runs the destructor. And now when we come back, this is where Rust starts to diverge, right? So we gave away our book, but we're trying here to use it again. So what happens? We get a compilation error. Because the compiler is tracking what did you own, what have you given away at each point in the program, and it won't let you use the things you've given away. And we track this on a pretty fine granularity, so you can give away one field of a struct, for example, or some fields and then reinitialize. But usually it's just a whole variable at a time. So this is somewhat different than kind of copy constructors, right? C++ has a very similar notion of ownership, but the defaults are kind of switched. So if I have that same example but transliterated into C++, it starts out the same. We have the memory layouts the same. And really, when I call publish, in a way, the signature here is the same. It's saying, give me a vector that I'm going to own. However, what happens on the other side, instead of giving them the vector that we have, we would invoke the copy constructor and do a kind of deep clone of the data, right? And now, from publish's point of view, it's all the same. They own this book. They can read it. They'll free it when they're done. But when we come back, we're in a very different state. We haven't given away our book. We still have it, and we could call it again and again and again. So you can do the same thing in Rust, of course. If you don't want to give away the thing you have, if you want to clone it, you can say that. This is Rust code again, by calling clone. But like I said, we've kind of switched the defaults around. So essentially, in Rust, doing a deep clone is explicit. The default, if you have something that has ownership and has a lot of memory associated with it, is to give ownership away, which is kind of the more efficient thing. So we do have a special case for things like integers, floating points. Those are what are called copy types, which is kind of like plain old data. And basically, as soon as you touch them, you're always cloning them implicitly because there's no real memory semantics associated with them. So, okay, so they're not quite copy constructors. Moves are somewhat similar to R-value references. At this point, we're getting past the C++ I learned in high school, so if I make a mistake, feel free to correct me, but I think I have the basic gist right. So if we change this program to use standard move, right, that's going to create an R-value reference to the book, and the net effect is going to be very similar, at least in terms of runtime, to what happens in Rust, right? We're going to copy over the stack fields, but we're going to take ownership of the memory. And again, publish has its own vector, which it can execute. However, again, we're in a, whoops, darn it. Sorry. That's the big danger with animations. However, we are, okay, forget it. We're in a different state when we get back, basically. The main difference is that the compiler in that variable book is still a usable kind of variable, albeit one in a kind of unspecified state at this point. And in particular, its destructor will run when we exit the function and so forth. So in Rust, that is not the case. When you give ownership away, it's as if you never had it. The destructor doesn't run. It's basically all tracked at compilation time. And that makes a big difference, not only because you find errors faster, but because when you're building APIs and things, it lets you use kind of, say, the zero size or phantom values as kind of tokens that you can give away, and then you lose access to them forever, and you can't use them again. And you can basically layer that to build more complex invariants in your APIs. So that's ownership. It's fairly straightforward. It is the most common thing, but actually in real life, or at least it's a very common thing, but in real life, usually if I give my book to someone, I'm not saying take it forever. I'm saying, here, why don't you read it and give it back to me when you're done, right? And that's usually what we want to do with data structures too. So that's where borrowing comes in. And there's two kinds of borrows in Rust. The first one, the most common one, is what we call a shared reference. It's written &t, and like the name suggests, it allows sharing, but we'll see that it does not allow mutation, because we said we want to keep those two things separate. So if we go back to our example, I've updated the type of publish. Instead of taking a vec of string, it takes an &vec of string, meaning a reference to a vector, right? And on the other side, instead of giving publish the book, I'm using the & expression. I'm sort of taking the address of book, but in Rust terms, I'm borrowing the book to make a reference which I can then give. So at runtime, this is just going to be a pointer. That's what an &vec of string is represented as. And we saw that it's going to disallow mutation. So I'm going to go into more detail on that after this slide, but for now, I'll put the little slash to show what I mean. So now publish can execute, and it has a borrowed copy of the book as a pointer to the book. You can use it, and when it's finished, no memory gets freed, right? Because it doesn't own anything. It's just borrowed it. And so we can then call it again and again because the book has not been invalidated by this. So let's see now this mutation thing. I have this theory that you can kind of, everything you need to know about Rust you learned in kindergarten, which is kind of what I say with don't break your friend's toys. Just kind of when you're sharing something, if you're borrowing someone else's thing, at least you really shouldn't be breaking it or writing into it and so forth. You should be nice to it. And that's kind of what happens with shared references, right? So when we first create the book, here this is a combined snippet in one function. When we first create the book, it's in a mutable state and we own it. So we can do things like call book.push, and that's fine. But when we enter into this block, and here I'm just using the block to scope the variable r, it doesn't have anything else, any other purpose. And we make this reference, we're putting the book into a borrowed state, in the compiler's mind, right? And that means that during this period where the reference is in use, we can't do mutations on book. So we couldn't call book.push. That wouldn't be allowed. And we similarly can't call through the reference to the book. We can't call r.push. Both of those would do the same thing, effectively, if we allowed it. So you see here that we have two paths to the same book. You can go through the original variable book, or you can go through R, and you could also copy R and make many references. And none of them allow mutation. But you also see that mutation in Rust is not a binary thing. It's not like this is immutable forever or mutable forever. It's really about, in this period, it's mutable, or in this period, it's not. And that's particularly here, because when we exit this scope, the variable R is going out of scope now, the borrow ends, and that means that we can, again, call book.push. That's perfectly legal at this point, since there's no references to it. So I should add one caveat. I've been saying immutable and mutable this whole time, and that's actually a little stricter. There are ways to mutate shared alias memory, but you have to go through special APIs. Essentially, you have to use unsafe code, which I'll talk about later. So an example where you would want to do that might be a mutex that's protecting some data. If you couldn't share it, you would just have the mutex in one thread. That's kind of pointless. So you would want to be able to share it amongst many threads and then have them each acquire the lock to gain access. That's an example of a kind of special API that enables mutation. But the default is, if it's shared, you can't mutate it. So if we go back to our first example now, this is the Rust version of a vector that we're going to invalidate, where we have a reference to its 0th element that we're going to invalidate. And we can see now that already the Rust compiler will rule this out, right? So if we make an element pointer here, we're taking a reference to the 0th element of the vector. That's going to freeze the 0th element, but also the vector itself, because it's the whole container, especially because the Rust compiler doesn't reason about indices in a very fine-grained way. And then we'll see we can't push on the vector anymore, because it's not allowed while this element pointer is out there. Okay, so that's a shared reference. And the other kind of reference is a mutable reference. And as you might expect, if you've been following this table, a mutable reference allows mutation, but doesn't allow for sharing, right? Let me show you what I mean. So here's my code example. I have a mutable reference to a vector here. It looks a lot like the shared reference, but it has a mute keyword in it. So signaling, we're going to do mutation now. And on the other side, instead of writing ampersand book, I write ampersand mute book. So again, if you're reading through, you sort of see where the mutations are happening. At runtime, this is exactly the same as a shared reference. It's just a pointer. But in the compiler's mind, it has a different significance. Instead of making that pencil go to an immutable state, it goes to a kind of locked state, where we're not going to allow access to the original variable at all. So now we can run our function. It can make changes through this reference, and they will affect the original variable. So we pushed onto the book, and we could call it again. We haven't given ownership away. And all these things can happen while we remain the owners, right? So how does it look? What does it mean to block out all access? Well, this is the same kind of format here, and we can walk through. And we see that initially the book is mutable, just like before. But when we make a mutable reference here, we're borrowing it mutably. Now it's a little bit different. Before, you couldn't do any mutations, but using either path, you could do reads. Now, if we try to use the original path, the book, even just to read it, just to get its length, we get an error. But if we try to use the reference, we can do anything we want. We can read it, we can write to it, we have full access. Right? And all of this is temporary, just like before. So when the borrow ends, we return to our original state where we can mutate the book. So the reason that we have it like this, there are a lot of reasons, actually. We found that this scaled better in various ways, but one of the reasons it's very easy to see is that when the mutable reference has sole complete access, it means you can do a lot of things like, for example, you could send it to another thread, and you can be sure that the original thread, no one's reading from it from the current thread, right? I'm not reading through it through a book, while another thread writes to it from R. That would induce a data race. And we'll see that later on. So there's one key idea here that has kind of been implicit that I want to make more explicit. I've been talking about how when you make a reference, it freezes this variable for a span of code. Like in this case, if I make a reference R to book of 0, I'm going to freeze the book until the end of this block, right? Starting from the let until the end of the block. That concept, this span of code, is what we call a lifetime. And in particular, it's the lifetime of this reference. And we give them names, although not within a function usually, as we'll see, but across functions. Sometimes you want to give names to them. So the full type here, it's actually part of the type of the reference, if you go into the full details. So where I wrote ampersand string, that's kind of a shorthand for saying a reference to string, and you figure out the lifetime. If we were going to write it explicitly, it might look like that, where we would say ampersand tick L string. So this tick L, the tick represents lifetime, and that means that a lifetime with named L, that's the lifetime of this reference, and it refers to this span of code. So we're saying this is how long the reference is valid for, how long it can be used. And the compiler won't allow you to have the reference outside of that lifetime. So you don't have to worry about this within functions. It's all implicit. And in fact, we don't even have a syntax for naming it within a function, although I'd like to add one. But across functions is very useful. So this is a function that returns a reference to the 0th element of the vector that you give it, right? And you see these annotations here. What these are basically saying is they're telling the caller, who doesn't know what the function's body is, what this reference is that is being returned. Where does it come from? It's basically saying, by tagging both of these references with the same lifetime, we're saying, I'm returning to you a reference to a string that I got from this argument v. And that seems pretty obvious here because there's only one reference as input. So there's really nowhere else we could have gotten it from. So actually Rust doesn't require you to write it explicitly in this case. We have elision rules that let you elide those things. But sometimes if you have many references, it can be important to clarify where the value is coming from and where it's not. And that allows us to kind of track these borrows across functions, right? So if we have this function first, and we have an example, here I'm borrowing book, but all I'm doing with the book, you see, before I was directly assigning it to a variable, so the compiler could easily see what was happening. Here I'm passing it to a function which is returning to us something, right? And the compiler can use these annotations, basically, or you, to track what's happening and say, okay, this reference, some subpart of this reference is going to be stored into R, and R is used in this block, so I can figure out that book is basically borrowed until that reference R goes out of scope. And that means, in particular, we're not going to allow you to say modify book here, even though there's no direct reference to book anymore. It got passed away. All right, so that's kind of the heart of Rust, essentially, what I just covered, the ownership and borrowing system, or at least one of the key parts of Rust. But the other key part is our approach to generic programming. And I think this is another place where we took a lot from C++, and we've tried to add onto it some other influences, in particular some of them from Haskell. So I called this section traits. Traits are very like the cornerstone, basically, of generic programming in Rust. And I think they're somewhat analogous to a concept. I'm sure the details are very different. And unfortunately, this is like clipping some parts of the display, but what that should say is trait clone. So we've actually seen this already. Earlier I said if you want to clone a book, you could call book.clone. What that was actually invoking was a generic method called clone that's defined in this trait. And so a trait is sort of like an interface that you implement for a given type. And they can have associated types, they can have different kinds of members. The most common one is a function. So here I'm saying clone is an interface with one method, and the signature of this method, so you see these different references to self. The first part, the ampersand self with the lowercase, that's declaring the receiver. So the this keyword is kind of implicit in C++. It's explicit in Rust, in part because there are different ways different modes kind of for functions. So in this version, I'm saying when you call vec.clone, I don't need to take ownership of the vector. I just need a reference to the vector in order to clone it. I just have to be able to read it. So one nice byproduct of that is when you read an interface declaration, you kind of see which functions will mutate and which ones will not, kind of like having a const receiver and so forth. And so the other version of self here, this is referring to the type. This is like a generic type parameter saying the type which is implementing this interface. Right? So when you call clone, whatever type you called it on, that's the type you get back. So here we have an implementation. This is how you would actually implement the interface, provide a version of it for some specific type. Now here I'm defining it for vectors. That first keyword that's cut off should be impl, I-M-P-L, like implement. And so we're implementing it for vectors, and the basic model here is very similar to C++ in the sense that for every different kind of vector, like a vec of U32, a vec of string, whatever, we will generate a custom copy of this code tailored to that type, right, fully optimized for that type. But the type checking version, how we handle that type checking is very different. We do the type checking once on this generic specification, not on each individual instantiation. Right? And that's where these requirements come in. So what this impl is saying is, here's how you clone a vector for any type t, provided that t itself is clonable. Right? And that's because when you clone a vector, you also clone all of its contents. So they have to be clonable. In the actual implementation, we can create a new vector here. That was something like we just saw, only I'm calling it v. And then we iterate over it. I don't have time to go into exactly how this works, but basically elem here is going to be, we're going to create an iterator, and elem is going to be a reference to each element in the vector in turn, right? So ampersand t will be its type. And on each of those references, I can call the clone method, and then I get back a value of type t that I can push into the vector. And when I'm done, I return the completed vector. So this is a very simple way to clone a vector. So most of the time when you're doing generic programming, you're first of all using traits and you're using methods, but we also have some traits that don't have any members at all, right? We call them marker traits. And these basically express properties of the type. They don't have operations themselves, but they will enable other things. Some of these are built into the language, some are not. So here's two examples, both of which have come up briefly in this talk. So the send one, the first one, that's not really built into the language, but that defines types that are thread safe and types that are not. And so, anything that kind of owns its data will be considered send. It will have an implementation for send. And it's using some various language features so that it's basically automatic. We have a conservative approximation for things that are thread safe, and we automatically have such a type be considered thread safe. So like strings, integers, and so on, those are all safe to send between threads, because when you send them, you also transfer the full ownership of their memory. But we saw earlier in my very first story, something like RC of string, where you have implicitly a kind of shared mutable ref count that's being non-atomically manipulated. That is not safe, and that does not implement send, right? And we have also an atomic version, which we call ARC, atomic reference count, and that one is send. And this is an interesting example because I mentioned that send is sort of automatic, so string and U32 don't need any extra annotations. Similarly, RC string would be ruled out by this conservative check, but arc of string is not automatically considered thread safe, but it uses unsafe code, which we'll get to later, to kind of opt back in and say, I know this looks dangerous, I'm manipulating this shared state, but I'm doing it in a thread safe way, so trust me on that. And then we saw copy. I mentioned that for integers and things, there's no ownership tracking. Copy is a marker trait that says any type that implements copy can be mem-copied from place to place. Right? So for floating points, integers, and so on, that works. This one is completely built into the language because it's so core to the type checking. Things that have destructors, like strings and RC strings, and also things that might have destructors in the future, like types that you define are not automatically copy. You have to kind of opt in to say you're allowed to treat this as copy. Yep. No. So the question was, RC string does not support send, so what would happen if I tried to add it myself, right, basically? And the answer is you can't do that because there are rules called coherence rules, which basically define who is allowed to implement which traits for whom. And so if you define a type, you are the only one that is allowed to implement traits that you can see, so to speak. So send is in the standard library. If your type and also string is in the standard library, so only the standard library can implement send or not implement it for string, let's say, and RC. But if you define your own type, then yes, you could choose whether to implement send or not for that type. Similarly, if you define your own trait, you could implement it for string, but you have to have defined one of the two. That way we prevent there from being conflicting implementations for a given type. Yes?
So basically, if there's two libraries, one of them implements trait, like provides trait, and the other provides type, there's no way to get those two working together without modifying the trait.
The question is, if there's two libraries, one of which defines the trait and one defines the type, they have to know about each other to a certain extent, right? And the answer is yeah, at the moment they do. We have different features for that in the package management system. So you can kind of have optional dependencies. One of them can have an optional dependency on the other so that people can say, hey, I want to, if you happen to be using both of these, then please do provide this impl. But it's an interesting challenge. It's one we've been working on a while because on the one hand, it would be nice to allow anyone to implement any trait for anything. On the other hand, then you can imagine like I have two different ways to hash a particular type, and I have two different hash tables that are using two different hashing techniques. And if they go and get confused about which one is in use where, everything goes crazy. So we've been trying to find a nice compromise between those two. I think we would like to enable it in some way, but we're not sure what the best way is yet.
I know it causes like a lot of trouble in Haskell sometimes.
Yes, Haskell supports incoherent things if you opt in, I think, but we don't allow you to opt in at the moment. Yes.
Wouldn't you be able to create a strong type that for the type that's going from a library, and then it becomes basically your type?
Yes, so the question is, could you, to solve this problem, create basically a strong type def, like a struct that wraps it, has only one field, and implement the trait for that? And yes, you can do that, and that's a common workaround. Sometimes it's not what you want. It's a little inconvenient sometimes. But actually, one part of the solution we've been thinking about is just to make that easier to do, since it's often good enough. Okay, so I want to talk a little bit about parallelism, and I'm going to lean here just a little bit on the last two sections, right? On ownership and borrowing and on generic programming. And the reason for that is that Rust actually has taken a big turn in its development when it comes to parallelism. We always wanted to have a language that had strong support for parallelism, but initially the idea was, okay, we're going to build it into the language. We'll probably take an Erlang-like approach, because that seemed like the only thing we could think that was going to work, where each thread has ownership of some memory and they can send messages to one another. But once the borrowing and ownership and borrowing system evolved, and the trait system, we realized we can actually move all of this into libraries, and they can leverage these two systems to avoid data races and give all the same guarantees that we thought that the language had to provide. So in fact, Rust, the language, knows basically nothing, or let's just say very little, about threads. It has a few intrinsics for doing atomic add and stuff like that, but other than that, it basically doesn't really know much about threads. And that all comes in at the library level. So it turns out ownership and borrowing we developed them for sequential programming, but they're really a good tool for avoiding data races. And if you look at the definition of what a data race is, it kind of makes sense, right? So a data race is this very common error where basically two threads share access to one piece of memory. At least one of them is writing to it, maybe both, and they're not coordinating with one another, right? They're not using any kind of ordering to do that. So this is basically the first half of this talk, right? Is all about, can we avoid sharing and mutation? So if we're avoiding sharing and mutation by default, we kind of don't have data races at all. And the only problems that you have to be careful about is when you introduce sharing and mutation back, like I said, maybe with a mutex or something. And that's when your API has to make sure that ordering is enforced. So here's a cool example. It's not cut off too badly. It's a parallel quicksort, and it's using Rayon, which is this library I was talking about earlier for doing fork join parallelism. It uses a few Rust features we haven't seen yet, so let me walk you through it. First off, the input to this is a mutable reference to a slice of integers, and a slice is kind of like an array. It has a number of i32s, those are 32-bit integers, sequentially in memory, and it comes with a length also, so we can do bounds checking. And we're going to do the usual quicksort thing. So we're going to pick, if it's only one, it's sorted already. Otherwise, we pick a random element and we partition to the left and right so that we sort kind of partially the elements. And then we're going to call this split at mute. And that's a library method that takes in a slice and a midpoint. And it gives you back two views onto the same memory, which are split at that midpoint. Right, so less and greater are now referring to kind of the left and right halves of this input. And it might seem like we're violating the prime directive here by having aliasing, since now we have kind of a path through vector and a path through less and greater, which can reach the same elements. But that doesn't happen because of the features I was talking about earlier. It's kind of low. But basically where the function declares, when it returns its references, we know where they came from. And so we know that less and greater were derived from vec because they're all annotated with the same lifetime, tick A. And so we can figure out that, therefore, while the less and greater are in use, the vector is considered borrowed, right? So when you call split at mute, you're effectively trading in. I had a reference to the whole array. Now I get two references, one to each half of the array, and I lose access to my original. Yep. Okay, so the question was, do I also specify that the ranges don't overlap? That's a good question, and I will get into it a little bit in a little next slide. But in this case, they can't overlap sort of by definition because we gave one midpoint, and we said 0 to mid and mid over, and those do not overlap, right? We didn't give two independent ranges, but yes, we might have a bug in our implementation, that's right. So, like I said, that's coming up actually. That's perfect lead into a later slide. So okay, let's assume for now that split at mute is correctly implemented and we have two disjoint views onto the original array. Then we can call this method Rayon Join. So join is a method defined, sort of a function, I guess, defined in the Rayon crate, which is a library. And what it does is it takes two closures as argument. Those are the parallel bars, right? And it starts, conceptually at least, starts a thread with each of the two threads, one with each closure, lets them run, and joins, waits for them to finish, and then it returns to you. But 1 second, I'll get to it. Under the hood, it's actually using a work-stealing runtime to do this more efficiently, right? And the key point is that these closures, the compiler doesn't know that the closures are going to run in parallel. All it knows is that whenever you have two closures that exist at the same time, they can't both have access to the same mutable state, because that would violate our prime directive, right? Our prime rules. So basically, here, the compiler will already check that the set of variables, at least mutable variables, the set of variables that each closure mutates, let's put it that way, is disjoint. So here we have less in one and greater in the other. But if I made a mistake, like say I used less in both, or vec in one, the compiler would flag it as an error, right? And all that happens kind of by the base system, and Rayon doesn't have to specify anything about that. And that sounds like an unusual bug, but actually I've made that mistake several times when I copy and paste code. Yep. Okay, so the question was, the closures, are they implicitly borrowing by mutable reference? That's a good question. So yes, effectively. What we do is we analyze the closure body, and for each variable, we figure out essentially a mode. So it can be by value, or by shared reference, or by mutable reference. And that's based on how you use it. So if they were only reading from less and greater, it would have been a shared reference. There are other cases it might take ownership, like if you take some vector and send it to another thread inside the closure. Yes, another question?
So why in this case you don't have to specify &mute when you call Quicksort in the closure?
So why don't you have to specify &mute when you call Quicksort in the closure? The reason is because if you have an &mute reference, and you give it to a function that needs an &mute reference, then it's a matching type.
Is the matching of the reference mode for the captures, does it take into account what to do with the closure? So for example, if I read and return the closure, I need to capture the value, and then if I don't, then I can do the reference.
Okay, so the question is, does the inference take into account what I will do with the closure? The answer is yes, it does, sort of. So the closures themselves, they're callable, right? And there's a trait for being callable. And so the way the model of closures is very similar to the C++ model, essentially. They're like a independent anonymous struct that has their various things that they touch as its members, and they may implement one or more of these various callable traits, and there are 3 of them. One for, one for by ownership, one for shared reference, and one for mutable reference. Right? And so when you declare your function, you're basically saying, like when I declare join, I am saying I need 2 closures, and I pick which of these traits based on how I'm going to use it. So in this case, I would take the ownership version, because I'm going to take these closures and send them to different threads. So kind of they're only going to get executed once. And so there's like a two parts. The one who gets the closure basically declares the conditions under which they will call it. Will they call it exactly once, or at most once, sorry? Will they call it sequentially always, but many times, or will they call it in parallel with itself? And then on the other side, based on what you touch and how you use it, we kind of pick which is the max you can support, and they have to match, or else you'll have an error. One more question in the back.
When you have this way of figuring out the kind of reference for closures, couldn't you just use it also for functions itself, and just figuring out if it's an &mute in a function for variables?
So the question is, could we figure out automatically when you want an &mute and when you don't, basically, for the variables?
Or just say auto or something like this?
And the answer is that we could, in some cases. If you get into the details, it can get quite tricky. Type inference is that way. But we're looking into doing some changes in that direction, but certainly not for mute. Maybe for shared references, but it's unclear. The thing is, it's actually really useful when you're reading Rust code to have a visual indicator, not only of where mutations will happen, but also of ownership and borrowing. Where am I giving ownership away? It lets you kind of predict compilation errors better. And so when we had that in the past, we actually took it out. We had some versions of it because we found that it was kind of actively confusing. You would expect a compilation error and not get one, or vice versa. So, see what? Oh, Well, you see it from the signature of Quicksort in this case, yeah. Yes, so that's the reason that it's called split at mute, is that you're declaring that you're getting back two mutable references. There's also a split at that doesn't have that characteristic. And so the thing I want to emphasize, I kind of brought it up earlier, but the whole reason that this works at all, the reason we can send mutable references to other threads without just because they're part of a closure is because of these rules that say when you have a mutable reference, there is no aliasing. Right? There are no other threads reading from it. Because even if another thread were just reading, if the new thread is writing, that produces a data race. Right? Okay. More questions, or are we happy? Okay, one more.
Sort of a design question. Do you plan on having a way to specify the type of a capture or a closure?
Do we have a plan? Do we plan on specifying the type of the capture?
Having a way to specify.
So I did. I think the answer is. I left out one thing, actually. There is a single flag you can use. You can write in front of the closure move and then the closure. And in that case, you are declaring that you take ownership of everything that you touch. And you do that specifically when the closure is going to be returned out of the function or in some way escape the current stack frame, because then you need to force there to be no connection, even if it would have been safe. No, we don't do it implicitly because it actually affects the semantics in some cases. Like if you have a single variable and you increment it, are you incrementing the one on the stack or your own copy? Which one are you changing? So move kind of declares, do you want your own copy of the variables or do you want to use the copy from the stack? And I think using move, you can actually emulate a full capture clause because you can move a reference and then you've effectively you've kind of declared how you want it. Okay, so I mentioned that Rust has a lot of different paradigms. I don't have time to go into all of them. We just kind of saw how fork join programming works and how it builds on borrowing. Oh, it also builds on traits. I got distracted by all the questions, but I should say that the one thing Rayon Join does say, it says I take two closures. It doesn't tell the compiler they're running in parallel, but it does require that everything they touch is sendable, right? And we talked about send earlier, because it's going to send them to other threads, so you better not be using an RC or something that's not thread safe in there. So it leans on borrowing and traits. And we also have other things, right? We have like message passing. This is built into the standard library. You can sort of imagine that message passing is just ownership transfer. If I have some data, I want another thread to have it, I just give ownership of it, and it's good. The only requirement is the data is send. And that was the thing that Ada ran into in the very beginning, right? And we support locking. So if you have read-write locks and normal mutexes, if you have two threads, the API is set up so that basically if there's some data that's protected by a lock, the lock owns that data, and hence, if you want to get access, you have to go through the lock, meaning you have to acquire the lock. So you can't forget to acquire the lock, and so forth. And we're doing actively now, I would say, a lot of work on lock-free data structures and future-style programming for asynchronous I/O, and so on. Okay. So let's talk about unsafe programming. So there was a question earlier about split at mute. And the question was, how do we know that it's right? And so basically the Rust type system has been designed to not be that smart. It has these relatively simple patterns of ownership, shared reference, and mutable reference, which is enough most of the time, but doesn't cover everything you want to do. And we've already seen some exceptions to that, like RC and so on. And for those things, the way we do it is we have the ability to opt out and go into a superset of Rust, which we call unsafe Rust. And basically, you write a block of code using unsafe, and then you can kind of break the rules. You can have essentially C pointers that point anywhere. They can be shared, they can be mutable, however you choose. And on the other side, the idea basically is not that you'll just take these unsafe blocks and kind of sprinkle them anywhere in your code that you happen to be getting a type error. I mean, you can do that. Some people do that. But that wouldn't be the best practice. Instead, the idea is that you're supposed to build an abstraction around it that is safe. Right? And so split at mute is an example of such an abstraction. And there is some responsibility there. So the question earlier was like, how do we know that they're disjoint? The compiler doesn't know. It trusts us that they're disjoint. Right? And we could design the API in such a way that we have a bug and we accidentally give overlapping ranges. In this case, like, the logic is fairly straightforward. We're pretty confident that they're not. But, you know, it can be subtle sometimes. But we know that we're not going to be able to kind of prove everything that humans can do, right? So that's not a goal of ours. It's just to kind of get the most of your code should not be using unsafe. And the nice part about this is when you have a problem, if you have a crash, you have a pretty good idea where to go looking, right? Those unsafe blocks and those unsafe abstractions, maybe you made a mistake in one of those. So I was trying to get some good statistics to give an idea of how often unsafe, I know you can't read that, don't worry, how often unsafe code comes up. I was working with Diane Hosfeld, who's someone who works on Servo, which I haven't talked about yet, but Servo is a project I'll talk about in a bit. And she has a tool for measuring how much unsafe code there is relative to other code. It turns out this is actually kind of a hard thing to measure, but we did our best. Within the Rust compiler, for example, we came up with this number. So the Rust compiler is 350,000 lines of code, more or less. It's actually excluding some part of it, but and approximately 4% of that is around is unsafe, meaning there are unsafe blocks kind of in its vicinity. And a lot of that is basically because we call LLVM. So if you think about it, calling into C code is kind of inherently unsafe, right? It can do whatever it wants. So there's not much we can do about that. So bindings tend to be a really heavy source where you bind to C and C++ libraries, tend to be a really heavy source of unsafe code. But that gives you a feeling. I mean, I would say in my daily usage, essentially I very rarely write unsafe code unless I'm working on Rayon, which is that library for work stealing, which yes, the core of it is written in unsafe. But even there, we've actually factored the library into two parts. So there's a core abstraction, which we don't change very often, that does the work stealing. And then all the like parallel iterator APIs and all that stuff, those are all safe. They're just layered on top, which is really cool because when we get pull requests from people who are, most of them are targeting that stuff, we don't have to review those as closely, right? A few basic tests is enough. We don't have to worry about data races and other subtle interactions. And that's a really nice benefit. So I guess that applies more generally, but I would say especially for open source where you have a whole lot of contributions coming in from a whole lot of sources and you don't know how the experience level of those authors, having a safe, unsafe distinction is very helpful. So, all right, I wanted to turn here and I want to talk some about putting Rust in production and what that experience has been like and so forth. So we've recently shipped Rust in Firefox. As I said, it was not a kind of completely no-brainer decision. For one thing, Firefox is a very big C++ code base, and we are not going to rewrite the whole thing at once, right? So what we tried to do, actually, before I go into this, what we tried to do in parallel with developing Rust is we were working on a project called Servo. And Servo is essentially a reimagining of if you did rewrite everything from scratch. If you said, okay, instead of taking Gecko, which was built in the 90s for unicore processors without GPUs, and we wanted to say, how would we render a web page now with today's computers? What would it look like? That was a big task, and we had a lot of early success, and I'll talk about it later, but kind of all of that informed the advanced features that we might want to bring into Firefox eventually. But when it came time to really put Rust in, we went looking for something smaller, something that could be basically the smallest amount of Rust code that we could actually put in so that we would then have to do all the other work, which is the make files, which is testing that we support all the different platforms. For example, Rust did not support WinXP at that time, and all these different things that Firefox targets. And so the first one turned out to be an MP4 demuxer. So this takes in an MP4 video, parses the header, splits it out into audio and video. And this code was written already in C++. It's actually it's a simple operation, but it's a common source of security vulnerabilities, this sort of thing, right? Because it's all this indexing, and there are these mean people who will like write MP4 files that are specifically looking at your code and the bugs in it, trying to take over your machine. And so Rust seemed like, well, that's a pretty good choice for that, actually. When this shipped, so this is now shipping, I should say. I think it shipped in, well, I guess here on the slide, you probably can't see it, but it says 2016 March. Since then, what you're looking at here, this big blue circle, is the telemetry of Firefox. So for users who opt in, some percentage of them, we send data back on kind of different measurements. And one of the measurements is we ran this Rust code in parallel with the C++ code. So we didn't trust it fully yet. and we checked that they do exactly the same thing. And this was how many times was that successful. So that's 100%. So that was pretty cool. And so this is run now about 1.2 billion times out in the world. And so this was kind of our first foray. We have a couple other similar things like this planned. I don't know if they'll make it or not. So one example is the URL parser. Another thing which accidentally, back when I was working at that company, Data Power, I remember that was if you were mad at someone, you were like, all right, it's your job to work on the URL parser now. Because it seems so simple, but it's really hard, surprisingly, especially when you get data URLs and all this other stuff. And another place where people can craft and try to attack your machine. So these kind of targeted areas are good places to introduce Rust in a sort of narrow way, right? And one of the things I wanted to mention here is that Rust does make this pretty easy, right? So we support the C ABI natively, and our structure layout can be made completely compatible with C structures. So you can very easily call it into Rust from C and into C from Rust, and vice versa, back and forth. C++ is a little bit trickier because it has such a rich set of features, right? And we don't support all of them. We're working on tools. The people who did this work who have also done a lot of work, as we'll get to in a second, integrating with the C++ code in Firefox, and they've had to support templates and the classes and the different data layouts and so on. So we have some tools for doing that, but it's still a work in progress. So what are the next steps beyond MP4 headers and URL parsers? So I mentioned this Servo project, which was kind of looking at how could we do the rendering engine differently. And there were two main things that are now coming from that project into Firefox itself. One of them is something called Stylo. And this is kind of an interesting story. So Stylo does CSS selection, which I don't know how much you know about CSS, but basically there's an HTML DOM, it's like a big tree, and you walk down and based on some predicates you assign different styles and so on. And it's kind of an embarrassingly parallel problem. And yet, when we tried in the past to do it, we failed to parallelize it. And there were a variety of reasons for that. Some of them were like Microsoft's compiler at the time wasn't compatible with something else, or there were a lot of annoying issues of that kind, but also stamping out and gaining confidence in the database, stamping out all the data races and gaining confidence in that was very hard, because this was basically manipulating all these DOM data structures that had been designed from the beginning to be single-threaded. And so people were afraid that they might never get it to work, and that once they did, maintaining it would be a real headache. And so it never landed. But now what we've done is we've re-implemented it in Rust, so that the main logic is happening in Rust code, which is using FFI bindings over to those C++ data structures. Right? And that makes the problem kind of easier, because you know that the Rust code is already data race free, and you have to just validate that the layouts and so on are correct. So this has actually been successful. It's showing speedups. And that's pretty cool. But one of the things that we noticed along the way of doing all this work for multicore is that actually that's already kind of a little bit dated, right? In terms of your machine, you probably have 4 to 8 cores, but you also have this big GPU sitting there has a lot more parallelism available to it. So one of the other big projects that we tried to do is to move rendering off of the cores and onto the GPU as much as possible, kind of following in the model of game engines. This is actually a movie. Let me see if it works. So this is showing different engines. That was 15, 9 frames per second, 5 frames per second. And then when we get to Servo, we come to 60 frames per second, and the CPU is very low. So you can see that there's definitely some benefit from doing that, right? And that, we hope to be moving that also onto Firefox at some point. So, right, so that's kind of I would say, other than what these features are, yeah?
Sorry, was that GPU programming done in Rust?
Yes, that was done in Rust. I mean, I assume that, I haven't looked that closely, but I assume that there's a certain amount of whatever people write GPU programs in, OpenGL and so on, to execute on the GPU itself. But
so you're not targeting GPU directly using NVIDIA's LLVM support, Rust?
I see. Not that I know of, but I'm actually not sure. It's a good question. But a lot of even though it sounds like it's all GPU programming, there's a lot of support that goes into it. So all the code around it is all in Rust, in short. The next thing I wanted to talk about was just kind of what Rust development process is like and the community of Rust itself. So one of the things that we've worked really hard on, and probably been one of the hardest things, is to be as open and as welcoming as we can to people from all backgrounds, and that means both technical and otherwise. But I think what we've been a little bit surprised with in Rust is we expected this to be a tool for C++ programmers. And it is to a certain extent, right? There are a lot of C++ programmers using it, or people who, or I should say systems programmers in general, right? C, C++, whatever. But there are also a lot of people who wanted to write that sort of code, but were concerned about the maintenance costs, about the learning curve and so on, and that they thought that if they actually ship this product to their customers and it crashes, it could be a lost customer, and they didn't want to take that chance. So a lot of them were working in, say, Ruby on Rails, or working in JavaScript or something, and Node.js, and they've been trying to experiment with Rust, and we're pretty excited about that. Kind of people from both directions. And that's helpful both for people using Rust, but also for getting a diversity of ideas about how to improve Rust. So I think a lot of those languages come with a very different expectation in terms of what the interface to the language and the user will be, right? So if you followed Rust at all, at least prior to the 1.0 release, you probably noticed at least one thing about it, which was that we changed it a lot. There was definitely a period, so I've been working on Rust 6 years almost, and it's been 2 years of stability, and I can tell you that before that, if I had some code that was 6 weeks old, I would just erase it. Like, it was not going to compile, it was going to be a lot of work. Might as well just rewrite it. That's exaggerating a little, but it is true that it definitely wouldn't have built. And we had to this is because we were doing a lot of experimentation, finding how the system should work. And that took us a while. And so when we declared the 1.0 release, we definitely wanted an end to that, right? We were tired of it. And so our goal is basically to say, it's not that we'll never change Rust, but that you will never be afraid to upgrade it, because you won't have a hard time getting your code to compile and so on. We can maintain compatibility, and we'll do that in perpetuity, right? But the danger is, okay, if we're going to maintain compatibility, can we keep innovating? Can we keep improving Rust? And how can we do that? And so we've been working on a system that sort of lets us do that in a very flexible way. And we call this our kind of feature pipeline. So if you want to add something to Rust, it starts out in the RFC phase. Right? And this is true whether you are in the Rust core team or whether you are somebody who's never worked in Rust before. If you have some cool idea you want to put into Rust, you write up a description of how it should work, and you put it up on our RFC repo. And you will get a lot of feedback. Actually, probably a better starting point before you post the description is to put it in the forums and iterate a little there. But regardless, every RFC that goes in kind of improves on the way before it comes out, is what we found. And even when we think we have an idea that's guaranteed perfect, we've got it all set up. And this is where it's really great that we have such a sort of diverse community, and also where we work really hard to keep the conversations pleasant. Because for a lot of people, including myself, if you post up some ideas that you had and you get a whole lot of blistering negative feedback, it's really discouraging, right? And it can prevent you, not only is it discouraging and you may walk away, but we may never find the better solution. So we're always looking for ways to kind of get the best of both worlds without sacrificing, if that's possible, to overcome the trade-off. So once we get through the RFC process, we move to this nightly release. So basically, the Rust compiler is kind of taking a model from browsers here. Right? So we release more or less every night. Sometimes the builds don't succeed for one way or reason or another. The current master branch, and you can use that, and people do. And then you basically have the bleeding edge. So that's where new features will get implemented there first. And if you use these unstable features that are still in iteration, you have to opt into it in your code. You kind of declare, okay, I'm using an unstable feature here. I know that my code may not build tomorrow. I accept that. And that's how you can then give feedback and influence the direction. So just because an RFC is accepted doesn't mean that the final state of the feature is known. Right? We kind of work on it over time. And then every 6 weeks, we will cut out a release, and we'll say, okay, this this contains only those set of features that we're happy with. All the other ones that we're still iterating on, those aren't usable from this stable release. So if you don't want to have the risk that your code breaks, you can just stick with stable and you're all set. And every once in a while, when we feel like a feature is done, then we will declare that it's stable and it'll go onto the stable release. So this pipeline has served us pretty well for letting things simultaneously be actively developed while keeping a core set stable. And we also do a lot of testing. So I mentioned like the crates.io repository. So for example, we run the compiler against all of it on a regular basis, checking to make sure everything still works the same as it used to, and so on. So that brings me to roughly the end of my talk. I want to leave you with a few things. First off, there's a bunch of resources. If you're interested in Rust, we've recently completed a new book, which I think is very exciting and has a really good direction for learning Rust and covering all of its various features. We have a users mailing list. We have an IRC channel. I think there's probably Slack and other things, although not official as well. And as I said, we work really hard to make sure that these are friendly places to come and ask questions. And the last thing I'll point you at is I have this screencast, collection of screencasts called intorust.com, which kind of take a similar style to what I did here, teaching you the different aspects of Rust and so forth. So one thing I should mention, because I always forget, I have a lot of stickers. If you like stickers, please come and find me. Also, if you have any questions about Rust and so on. So, all right. Does anyone have any questions now, I guess? But.
So, thank you for the great talk. I'm interested in the state of metaprogramming in Rust. I know about macros. They're really, really powerful, but they are not namespaced, for example. So it's hard to export them between crates. Also, there are no variadics, no type-level integers. So I would like to know what kind of work is being done in that direction, because it's something that I'm passionate about.
Yes, metaprogramming is, I imagine, something a lot of people are curious about. So so Rust has two main directions for metaprogramming. So you mentioned macros. I'll kind of talk about the two things first separately. So if the current macro support, I don't know how many people here have worked in Scheme. Any? Me? Okay. It's very similar to Scheme macros, if you know those, and particularly macros by example, which are very powerful. And they let you kind of write arbitrary syntax, essentially, inside of Rust code. So, however, the current ones, they're very powerful, but they also have a lot of shortcomings. So the namespacing was one. There are others too, like the hygiene support is lacking, and so forth. So we've been working on what we call macros 2.0, which is basically an improved version of the macro system. It's exactly an example of using this stability system to its full extent. I think the PR has not yet landed. There's a PR with the initial implementation, but of this macros 2.0 stuff that's in the queue and will be coming soon. But a lot of the namespacing features are actually already there if you opt in on a feature into the right feature gate. I don't know the name off the top of my head. So that allows you to basically use normal imports and exports to name macros, and it works backwards compatibly with the old macro system. We're also working a lot on procedural macros, which if you've used Scheme, you're probably familiar with. So macro rules that I've been talking about is basically like a interpreted matching language that lets you pull out things and paste them into Rust syntax, kind of like handlebars, but different. Not like handlebars at all, but it sort of looks like that. And the procedural macros is really you just write Rust code. It's like a plugin, and the compiler will invoke that code and execute it, and you can return whatever you like. And we've stabilized the first version of these, which we call derive. So I didn't talk about it here, but you often have these traits like EQ or hash. They're just really tedious to write for your structs. And derive is basically a way to say, run this code, here's the struct definition, generate automatically a reasonable default implementation. And now, that used to be built into the compiler. It's now something you can write in a Rust code. You can put that crate on crates.io and add it as a dependency, and everything kind of just works. And so that's stable now. So that's macros. Procedural macros are coming up, I should say. They're kind of part of the same macros 2.0 infrastructure because it's all tied into the hygiene system. As for other metaprogramming, right now we do not support constant generics very well. However, that is definitely high on our priority list. So one of the really excellent compiler team members, Eddie Bertuski, actually I have no idea how to pronounce his last name, I shouldn't even have tried. Eddie B on IRC is actively working on it, and I'm confident therefore that it will be done soon. But that will allow us to kind of have some basic support. And we've been working on more advanced support as well. But I think extending the trait system is something that we have a lot of ideas, and one of the big projects we're doing besides const generics is actually reformulating the trait system in a more formal way, because we found that the current system, it's time for us to have a kind of more core expression of it so that we can better understand all these extensions like specialization and so on. So there are a lot of things you can do in C++ generics that you can't necessarily do in Rust yet, but we do aim to support them.
Cool, thanks.
Thanks for the talk, and so congrats on Rust being stable for 2 years. That's cool. C++ has been there for arguably between 20 and 30 years. And what seems to have happened is over time, probably when two years after C++ had this kind of like stability, they thought that it was pretty much everything was a good idea that was there. But 20 to 30 years later, turns out there are better ideas, and incorporating the better ideas and maintaining backwards compatibility is incredibly hard, especially if you want to do it in an elegant way. So C++ is in the state right now where it's very complex, and new features, there's a lot of pushback just naturally because of backwards compatibility concerns and increased complexity. So how is Rust going to not fall into that same state?
Good question. That's actually a topic of hot discussion, not surprisingly. We've been talking about, I should say here I'm going out on a limb because these things are not settled by any means, but the way that I see this happening is we've been discussing introducing something which we call epochs, which kind of corresponds to like C++ 11 plus 14, sort of, in the sense that these would be essentially different, kind of like different versions of the Rust language, but the compiler would continue to compile the older code, and we would gradually transition from one to the other, but when you move to the new epoch, essentially a whole bunch of deprecated things become errors. Right? So we would be trying to phase out things that we don't want, and sometimes that's just because we think it's an anti-pattern, sometimes it's because we think that it's, we want to make room for a better way of doing it, and to do that we have to kind of first make the old stuff go away. We don't want to break any existing code, so the idea is that the packages that are up there they have no epoch, they will default to like the oldest one, and they will continue to compile as they ever did, and they should be completely intercompatible with new packages, because all of these changes tend to be kind of in the syntax level, let's say. And you can usually, at least we would not want to do any changes that don't allow you to communicate with older code in any way, like they really change the representation or something in some way that's not backwards compatible at all. But this would allow us to kind of deprecate older styles of code that features we think people shouldn't be using, and make room for newer things. But we're still discussing it. I mean, there's definitely a concern that perhaps the message becomes too subtle of stability, and people are afraid that they don't want to upgrade because they think that it will break their code and so forth. So we have to make sure that it's understood, that in fact, all the old code keeps working. The world is not split. Your dependencies don't have to upgrade just because you did, and things like that. We also have to make that true. But any more questions?